All right, folks, we're going to go ahead and get right into the lesson today. I don't want to waste time and just kind of get the key points for today's lesson across to you. So to start off with, you've got these terms up here that we should be pretty familiar with, actually every term that I have up here. So let me just kind of go over those real quickly. A regular polygon is a polygon whose sides and angles are all congruent. Now, we've talked about this earlier this year, but I need that to become more like embedded in your mind frame that, when I hear of a regular polygon, think of all the sides, all the angles congruent. Now, if I can give you a hint, a helpful hint, here's what it would be. Any type of polygon that's the first thoughts that comes to your mind is probably a regular polygon. Like, for example, if I say a triangle, you might be thinking of like a yield sign, okay? Or an equilateral triangle. Well, that's a regular polygon because all the sides and all the angles are congruent. If I say an octagon, you might be thinking of a stop sign. Well, guess what? All the sides and all the angles are congruent. It's a regular polygon. So usually when we think of a certain polygon, they are regular polygons if we are used to seeing them on an everyday basis. So again, regular polygon, all sides and angles are congruent. If I say an interior angle, it's just an angle that would be on the inside of the polygon. So I'm pointing here to the interior angles of this pentagon right here. Okay. An exterior angle, we've discussed earlier this year, that is to extend a side out, and that angle it's formed is considered an exterior angle. Now, I can have two exterior angles from a common vertex. If I was to extend this side out right here, this would also be an exterior angle. But what do we notice about these two exterior angles? They're vertical angles, so they're going to be congruent to each other. Okay. So again, what is an exterior angle? It is to extend a side beyond the vertex, and that angle right there is going to be the exterior angle. Okay. I'm going to be using the term diagonal in the next section right here. And so what is a diagonal? It's a segment that connects two non-consecutive vertices. Okay, you guys know what a diagonal is. You've drawn diagonals many times over through elementary school and on up. So that's what a diagonal is. So now I have a chart down here, and the purpose of this chart is to develop your understanding of a formula, actually a couple of formulas that we're going to be deriving from this chart. Okay, so let's just go down through the chart here, and you'll see patterns form, which will eventually lead to formulas. So the first figure's name we all know is a triangle. Okay. If you're not sure how to spell some of these, I will spell them out for you so you can see them. The next one, the most specific name, is a square, which probably what a lot of you were thinking about. But I want to start just in general. If I was to throw any type of four-sided figure in that box right there, what would it be called? It would be a quadrilateral. Okay, quadrilateral. The next one is a pentagon, 5 sides. Okay, actually we can fill that out as we're doing this. 4 sides, 3 sides. Okay. And I know the question is going to pop up, do I have to have these memorized? Yes, you should know each of these polygons that I'm going to list off here. There are maybe 1 or 2 that you're going to have to memorize, but the rest of them you should already know. The next one, a 6-sided polygon, is a hexagon. People usually get the 6 and 7 mixed up. Okay. The 7-sided polygon is a heptagon. The 8-sided we all know is an octagon. The 9-sided, my personal favorite, nonagon. Okay. And if I flip over to the back side, how many sides is this? I think this is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 would be 10 sides, decagon, like a decade. Now this one is a 12-sided figure, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 sides to this one. This one is called a dodecagon. Okay. Might be thinking, why did he skip 11? 11-sided polygon isn't usually stated in the textbook. Okay. I believe it's called a hendecagon, is an 11-sided polygon. But again, if it has 11 sides, they're probably going to call it the next thing. If it goes beyond these, they'll use the number of sides they'll call it an n-gon, meaning that they will replace the n with a number, 25 gon for a 25-sided polygon, a 17 gon for a 17-sided polygon. So how many sides does an n-gon have? It has n sides. Okay. All right, now going back to the front side, again, I hope you paused that if you weren't able to keep up there. On the front side, this is not meant to be a trick question. How many triangles are there in a triangle? There's just one triangle, okay? Now that term diagonal is going to come into play in the next couple of figures here, and I wouldn't draw this in, folks, unless you feel like it's necessary, but if I draw as many diagonals in from one vertex, I can determine how many triangles can fit into one figure, one polygon. So if I go ahead and do this right here, how many triangles can be formed? There's 2. Okay. Now some of you may be thinking I can draw another diagonal in over here, but the thing is, these angles that make up this triangle and the angles that make up this triangle are going to help us figure out the sum of the interior angles of the polygon. Okay. If I draw in another diagonal, there's going to be angles at the center, and that doesn't help me figure out the sum of the interior angles of the polygon. Okay. So again, I go from one vertex here, and I'm going to draw in as many diagonals as I can. And so right now I'm seeing 3 triangles for the pentagon. Okay. For the hexagon, if I go from one vertex, I am seeing 1, 2, 3, 4 triangles. Are you seeing a pattern form? Better believe it. There's going to be 5 for the heptagon, 6 for the octagon, 7 for the nonagon. Decagon's going to have 8. Be careful in this next one. How many does a dodecagon have? There should be 10, right? So what is the pattern from the number of sides to the number of triangles? Each one has 2 less. So n minus 2, the number of sides minus 2, will give you the number of triangles within the figure. Okay. Now let's go back to the sum of the interior angles. For a triangle, what's the sum of the interior angles? Well, we've known for a long time it's 180 degrees, right? Okay. Now, if there are 2 triangles in the quadrilateral, this would be 360 degrees. Okay. If there are 3 triangles in the pentagon, this would be 540 degrees. Okay. 4 triangles, that would be 720 degrees. Again, 4 times 180 is all I'm doing there. 5 times 180 gives you 900 degrees for the heptagon. 6 times 180 gives you 1080 degrees. 1160, 1260 would be the next one for the nonagon. Then back to the decagon, we have 8 triangles. So for 8 triangles, you have 1440 degrees. For 10 triangles, that would be 1800 degrees. And now comes the formula here. What did we do in each one of those situations? We took the number of triangles and multiplied it by 180. The number of triangles multiplied by 180. So I'm going to take the number of triangles times 180. And that's the formula that you're going to use quite a bit, at least in this first section, but I don't want you to forget it. We're going to revisit that throughout the course of the year. Now, the next part says the sum of the interior angle measures of an n-sided convex polygon is that formula right there. The sum of all the angles of a polygon will always be calculated using that formula. Okay? So, I'm going to skip the polygon exterior angle sum theorem for just a moment, and let's move down here. So I see a pentagon. Now, I could go back and look at the front side of my paper here, but I want to practice my formula, that n minus 2 times 180 formula. Okay? What did n represent again? The number of sides. So I'm going to do 5 minus 2 times 180, which gives me 540 degrees. Now, how does that help me? Well, if I go ahead and want to figure out the value of x within this figure right here, I can go ahead and add up all those angles, 2x plus 142 plus 2x plus 3x plus 14 plus 3x plus 14 and set that equal to 540 degrees. The sum of all the angles of a polygon has to equal, if it's a pentagon, has to be 540. Doesn't matter the shape. Okay? So if I move on to this six-sided figure, the hexagon, the same thing is going to be true. I'm going to use the number of sides minus 2 times 180, and that will give me 720 degrees. Okay? And if I add up all of those angles inside the figure there, x minus 4 plus x plus 6, x minus 3 plus x plus 7 plus x minus 8, I'm running out of room, plus x plus 2, okay, that will all have to equal 720 degrees. Okay. Now, remember, I think you guys are pretty good at the algebra portion, which is why I didn't solve the last one or this one, but combine your like terms, folks. Combine your like terms before you go ahead and finish it up there. Okay? So, going back to the problem here, the directions do say determine the measure of each interior angle of the polygon. So when you solve for x, so like for example, we end up getting, I think the x down here ends up being 37 degrees if you solve for x. You just plug it back in, and angle K here is going to be 2 times 37, which will be 74 degrees. Okay? All right, so again, that's how you set the problem up, and then from there it's just algebra based after that. Okay? So again, what is the sum of the interior angles of a polygon formula? N, which stands for number of sides, minus 2 is equal to 180. Okay? Now, let's continue on. We've got a couple more practice problems here that deal with this idea. It says here that Penny is building a house using a floor plan that she has designed. What is the measure of angle ABC? Now, what I want you to see as you look at this picture right here is that this shape, okay, zoom in a bit here. This shape is meant to be a regular polygon, meaning each of these angles are going to be congruent, okay? So, if you want to figure out the measure of one of those angles, adjust the picture here a bit, okay? If you want to figure out the measure of one of those angles, there you go, that looks better. All you're going to do is you're going to take that formula that we just talked about. That helps you find the sum of the interior angles, and you can divide it by the number of interior angles, which is the same as the number of sides, and that will give you one interior angle of the regular polygon. So if I were to go ahead and do something like this, in this case there are 6 sides, so 6 minus 2 times 180 divided by 6, that ends up giving you 120 degrees. Okay, so this angle, as I look a little bit more closely at this, angle ABC, as I trace that angle, it's an obtuse angle. My answer was 120 degrees. That's a good thing that I got an obtuse measurement for an obtuse angle. Okay? So, again, if you take your sum of your interior angles divided by the number of angles or number of sides, that will give you one interior angle because they're all the same measure. Okay? I'm going to skip the next one right here just because it's the same type of problem and I want to save time. I think you guys probably got that. If you didn't, come and see me and we can talk it out a little bit further. So this next one, I'm going to give you 2 different ways here in a moment that you can work a problem out like this. This one says the measure of the interior angles of a regular polygon are given. So we know that the interior angle is 144 degrees. Determine the number of sides of the polygon. So what I'm thinking right now is this. If that's the angle, the formula to get that angle we just said was this. Take the sum of the interior angles and divide it by the number of angles. Okay? Now I know that looks kind of expansive. That looks like a lot, right? Okay? So how are we going to make this simple? Well, right now everything is divided by n. So what I would do is I would multiply both sides by n it gets rid of that n right there, and that will leave us with this. 144n equals n minus 2 times 180. Okay? Now, from here, if I distribute that 180 into the parentheses, you end up with this, 180n minus 360. Now we're right. I mean, really, after we undid that division right there, everything else is just basic algebra that we've worked on so far. So I would go ahead and subtract the 180n from both sides. And in doing so, well, what's that give us? Negative 36n is equal to negative 360. Okay? And then how do we get n by itself? We can divide by negative 36. So how many sides does this polygon have? If the interior angle is 144 degrees, there'll be 10 sides. Oop, didn't see the bottom part there. There'll be 10 sides. Okay, so that would be a decagon. All right. Now, I said I was going to tell you another way that you could solve this, and there's actually a quicker, faster way to solve for the number of sides given one interior angle. But in order to know that way, I have to go back to our chart. So here's what I want to do. I'm going to go back to the very beginning of our chart here. Okay, and we're going to look at the figures here. Now, let's assume, for argument's sake, that each of these angles is congruent here. And we've been talking that the sum is 180 divided by 3 gives us 60 degrees. So I'm going to put down that this is 60 degrees right here. Okay? And all I'm going to do is I'm going to extend one of the sides beyond at each of the vertices. Okay? So with 3 interior angles, I'm going to extend it out and make 3 exterior angles. Now what you'll notice here is that each of these are supplementary. They form a straight line. So this angle here is 120 degrees. This angle here is 120 degrees, and this angle here is 120 degrees. Well, if I add up all those exterior angles, what does that equal? That equals 360 degrees. Okay? Now let's go to the quadrilateral here, and I'm going to extend out 4 exterior angles, one at each vertex. Okay? Each of these angles is going to be 90 degrees. Now, if you take 90 degrees and multiply that by 4, that also gives you 360 degrees. So right now I'm thinking, hey, could it be that the sum of the exterior angles of any polygon is always 360? And here's what I'm going to do. I'm going to do it one more time just to test my theory to see if this is true. Okay? Now, in order to get this, I'm actually going to come over here and do this. We know that in the pentagon, 540 is the sum of the interior sides, or interior angles. So if I take that 540 and divide that by 5, that gives me 108 degrees. Okay? So that means that each of these interior angles, which all look obtuse, are all 108 degrees, every single one of these. Okay? Now from there, that would make the exterior angle 72 degrees. So if you take 72 and multiply it by 5, what does that give us? Again, that gives you 360 degrees. Okay? So, really simply, the one formula that we have to memorize, the sum of the interior angles, number of sides minus 2 times 180, the sum of the exterior angles is just 360. Okay? So if you can remember that, that's helpful right there. Now, going to our problem that we had that we were looking at just a moment ago. Okay? We said that if we wanted to find one interior angle, we'd take the number of sides minus 2 times 180 and divide that by the number of angles. Okay? And I showed you the algebra how you could figure out the number of sides. Now, I'm going to ignore this for right now, and I'm going to do this. What if I wanted to use the exterior angle formula? Okay? Here's what we could do. Remember your interior angle and your exterior angle, they are supplementary. So if the interior angle is 144, what's the exterior angle going to have to be? Well, if I take 180 minus 144, that gives me 36 degrees. Okay, that's the exterior angle. Now from here, think about it this way. If every interior angle is the same in a regular polygon, then what do we know about every exterior angle? It's also the same, okay? So if you take 360, the sum of the exterior angles, and divide it by the number of exterior angles, which is equal to the number of sides, that will have to equal one exterior angle, okay? So kind of like this last one over here, we're dividing by n. What do? I'm going to multiply both sides by n to get rid of that division. What's that give me? Well, 360 equals 36n. And if you divide through by 36, we get the same exact answer. Okay? Now, do I care which way you do it here, folks? No, I don't. Okay? I want you to know one way and do it well. Okay? So, doesn't matter to me. Know your formulas. Know how to do one of the ways well. Okay? Now, to finish things off here, I've got basically two more types of questions I'm going to show you here. In this figure right here, we've got 4 exterior angles to a quadrilateral. Well, here's what I want you to know. These are really simple. What is the sum of the exterior angles of a polygon? It's always 360. So you can just set up that equation right there. The sum of those exterior angles will always equal 360. In the other one, it's the same thing, but this time it's a pentagon. But guess what? The exterior angles still add up to be the same thing. So the sum of these exterior angles will still equal 360. Okay? All right, so that should be your equation for that one as well. All right? And then the last one, keeping in mind with this idea of exterior angles in a regular dodecagon, means all the exterior angles are the same. If you take 360 divided by the number of exterior angles, that will give you one exterior angle of a regular dodecagon. Okay? So again, the big ideas: regular, congruent sides, congruent angles. The sum of the exterior angles, no matter what shape it is, will always be 360. How do you find the sum of the interior angles of any polygon? N minus 2 times 180. Okay? So if you got those three things down, everything else kind of comes out of that right there. Anyways, thanks for sticking with me here. You have some practice problems here. Okay? Down here at the bottom. 1 through 4, 6, and then 13 through 16. Have those done for me for Monday. Thanks, guys. Bye.